So the first notebook that we are going to discuss together is the one on Aperture Photometry with MIRI. And as it has been presented at the beginning of today's webinar, you are on this page and you can go in on the folder JWebbinar prep, point source imaging, and then you select the notebook. You might not have all the files here, but don't worry, they will be downloaded when we execute them. So the one that we are going to discuss today, I'm going to use here is the live version, but if you feel free to use the solution one if you don't want to code with me. Okay, so let's go ahead, double click, and let's make this disappear. Okay, so as I said again, let me stress that this Aperture Photometry is very basic. It's not very difficult to perform. And most of what you see here in this table of content seems a lot of things, but I just want to give you an overview of the JWST data, or specifically on the MIRI data. And also I want to explain a few tools that I am going to use today specifically the PhotoUtils tools. That is a public available software. So let's start with this notebook. So again, the first thing we're going to skip through are the imports of the Python library, the configuration of the plot, a few functions that are just, okay, a few functions we're going to discuss. And here we have a dictionary that is called filter underscore full width maximum. This is the full width maximum of the PSF in the two filters of the images we are going to analyze today. And I will explain you later why we're going to use these two values. Here, you can go ahead and download the data. So we are going to download two files. The first one contains the images. You will see in your folder 8 images, 4 for the 560W filter and 4 for the 770 filter. Each of these two these two datasets was simulated using a 4-point detail pattern strategy. So something that we recommend when you're interested, for example, in point source imaging. So this will allow you to test your code. And then the second zip file that we're going to download contains two catalogs that were made by the stage 3 Python. And we're going to use these at the end of this notebook to perform the photometric calibration. Okay, so it should have completed for all of you. So we can go ahead and hit Shift Enter here. Just create a few dictionary with the names of the files that we're going to use today. So the first thing that I want to go through is to have a look at the image of the MIRI imaging data. And to do this, we are going to open one F60W image, and we are going to open it as a JWST data model. If you're interested in what this JWST data model is, refer to the JWebbinar number 1 products, in which there is a very nice description of this. So to start this, we just have to type to read the image as data models. We type a data models.open, then image names, the name of the filter, and then here I will select the first image, but feel free to use either 0, 1, 2, 3, so one of the 4. You go ahead and read it. In the next slide, in the next cell, what it's going to do is just to set up a few parameters for a plot, and then call this function that does a plot with the classical Python matplotlib tools. So this is how a stage 2 image of MIRI looks like. And you can see here, on the right, there is the largest area. That is the one that is actually called imager. On the top left, there is the part that is usually dedicated to the layout coronagraphy. And on the bottom left, there are 3 regions that are those that are usually dedicated to the 4-quadrant phase mask coronagraphy. Okay, so the first thing that I want to show you is how to select the pixels that you want to use during your analysis. And to do this, we're going to use the data quality flags. I linked here a description of what they are, how you can use it. Basically, on the JWST data model, there is an extension that contains these integer values, 1 per pixel, and give you an assessment of how reliable is that pixel. For today, we're going to use only 4 DQ flags. but which one to use is up to you and to your science. Again, have a look at the documentation for to find more about that. So we're going to use all the DQ flags that are equal to 0, 2, 4, and 6. So either a good pixel, partial saturation during an integration, jump detected during integration, which means likely a cosmic ray hit your pixel, and a combination of flags 2 and 4. As you can see, these are integer value, and you can also have combination of them. So it might be a bit problematic to remember all the meaning of this DQ flag, but you can use this function called DQ flags to mnemonics that convert these values into more user-friendly names. So for example, if you run this cell, you see that 2, 4, 6 are flagged as saturated, jump detected, or both. So now, if you run this cell here, what you see is what it does is to flag all the pixels that do not have a DQ flag that is equal to any of these 4 values, and these pixels are gonna be flagged at not a number. So I will always remember that I do not have to use them. So I already ran this cell, and you see that it seems that about 30% of these pixels should not be used. So if we go ahead with the next cell and we have a look at the image, how it looks like after the masking, and you can see that there is quite a difference from before. And as you can notice, the regions here associated to the 4-quadrant phase mask coronagraphs have disappeared from the image. So the reason is the following. The optical system of the 4QPM coronagraph is different from that of the imager. And because of the way of the optical elements that are part of this coronographic system affect the light transmission of photons that are going to hit the detector, the calibration of these 4QPM regions is complicated, and it is specific for the coronagraphs. So even as you have seen in the previous plot, the photons do actually hit the detector, and they are imaged when you use MIRI in imaging mode. These 4 regions, these 3 regions here dedicated to the 4QPMs should not be used to analyze a stage 2 image when MIRI is used in imaging mode. This is not, as you can see, the Lyot region is still there. That usually it is dedicated, this region, to the Lyot coronography, but the Lyot coronography, as on top of the optical system that is typical of the imager, has an occulting spot in addition to that. So it's just something that blocks the light. So besides the few edge effects that might occur here, the rest of these areas should be used as the rest of these imager parts. Another thing that you can see here are these 2 columns. From our test, ground-based testing, we found that these 2 columns here that are flagged seem to be coupled, and so they should not be used for the analysis. So always remember to have a look at the DQ flags in general, and especially for MIRI if you use that in imaging mode. So, okay, so now we have done with the introduction to the MIRI data. So now we can go into the detail of the creation of the astrophotometric catalog itself. So today you can use whatever tool you want to do Aperture Photometry, but today we're going to use PhotoUtils, and I linked the documentation for these Python tools. PhotoUtils provides a lot of tools that can be used for a variety of things that you want to do. And today I'm going to show you only a few tasks that may be interesting for your analysis. So the first one that I want to show you is how to subtract the sky background directly from your MIRI image. And as you know, the JWST background will be dominated by mainly 3 components. That will be the emission of the zodiacal clouds of the solar system, the emission of the Milky Way, and the self-emission of the telescope. That is going to be important, especially at the wavelength longer than 10-15 microns. So the sky background is just not a pedestal that is added to all your pixels in your image. It's something that may varies across the images. So you don't want to subtract just, I don't know, the mean or median value of the whole entire image as the sky background. So to what I'm going to do today is to use a function that is called background 2D. And what this function does is to divide your image in n times m subregions. It then estimates the background in each of these regions, and with the grid so created is going to be to interpolate the sky background in each of the pixel values. Then this image is going to be smoothed with the median filter. So if we go here, I listed a few of the parameters that you might want to set up for background 2D, but I'm going to get through it in the set. So the first thing that we're going to do is to mask all pixels that are set as not a number or are not finite. So those pixels that we mask with the Q flag, for example, we do not want to use them at all, not even for the sky background. The second thing here that I highlighted with my cursor is the sigma clip. So here, this is just an instance that is going to be used by the background 2D function to do a clip of the pixel value that we are going to compute in each of these n times m subregion of the image that we are going to split into. Then there is this background. That is the background estimator. Again, how the background is going to be computed in each of these subregions. And for today, I'm going to use this mode that is using the algorithm that is described usually use described in DAO-Photo. It's called algorithm. DAO-Photo is a famous tool by Peter Stanton. And so with this algorithm, the mode is defined as 3 times the median minus 2 times the mean of the pixel values. So if you want to compute the sky background, we just have to call our background to the function, and the result is going to be saved into this object here. So what you want to provide in input is the image. So image F60W is the one that we read before as a data model, dot data. So we take the extension with the data from the JWST data model. Box size, the size in pixel of the n times m subregion that we are going to split into our image. And for today, here we can use 20 and 20. Filter size, the size of the in pixel of the 2D median filter, the window of the 2 median filter that we're going to use to create a low resolution background map. And for this example, we can use 3030. This is the sigma clip instance that we want to use. And so we just copy the name of before. The background estimator, so that's going to be used to compute the background in each cell. And we use the one we defined before. And the coverage mask, so which pixel we are going to use. And so this is, we put our mask created at the beginning. Then our sky subtracted image is going to be our original image dot data minus sky F560W dot background. And then in the end, if you run it, we will also plot the sky subtracted image. If you go ahead, you can see that this is the resulting image. It seems quite okay. It doesn't look that much different from the one that we've seen before. The only thing that you can notice is that if you hover with the cursor on an empty space, you can see that the sky background level is at about 0, while before, as I plotted here, it was at about 1.03 megajoules per steradian. This is the pixel unit of this stage 2 image. Okay, so this show you how to create a very simple background model of starting from your image. Of course, this is not going to be always possible. For example, if you have an extended source, this might be tricky to do, so you might want to use other techniques or dedicated background observation that can be planned as part of your observing strategy. So now we can go ahead and work with on the Aperture Photometry itself. The first thing that I showed is that how to subtract the sky background from the image, but we actually are not going to use the sky subtracted image when we are going to do the Aperture Photometry, because we are going to evaluate the sky background for each source locally in an annulus around each source. The third thing, as I said during the presentation, that you want to do is to search for the sources in your image. And to do this, today I'm going to use this DAO*finder function that is, again, an implementation of DAO-find algorithm of step-from task. DAO*finder searches an image for local density maxima that have a peak and an amplitude that is greater than a specific absolute threshold on the image, and that have a size and a shape similar to that of a 2D Gaussian kernel. So as you can understand, this function is going to search for maxima that are above the fixed threshold. So if you use your original image with the sky level that it is whatever it was before, So you might have, since the sky varies across the image, that if you set one specific absolute threshold, you might end up with a different finding, the different detection across your field of view. So in one side of your field of view, you might have less detection than on the other side, just because the background is slightly different. So the absolute threshold applies different selection on the Starfinder. So for today, what we are going to do is to search for sources that are at least 5 times above the sky RMS, sky background RMS that was computed before by Background 2D. And this is what is written here in the first line. In the second line, we are going to read this we are going to set up this full width maximum of the F560W filter using this dictionary. So we're going to use this the full width of the PSF in F560W for the MIRI imager as the full width of the 2D Gaussian kernel that's going to be used by the Starfinder to search for sources in the image. So to do this, we just type filter full width function, the dictionary, then get, and then here you put the filter name. And since we have a data model here, I can take this piece of information from the JWST data model itself, just type in meta.instrument.filter. So now we can create the DAO Starfinder instance as follows. So we type phototils d.DAO Starfinder. Then you want to set up the threshold, that is going to be threshold underscore F60W. The full width maximum of your kernel, that is the one that we just discussed, and then this flag set to true. That means that the Starfinder is not going to find sources very close to the edges, otherwise we might have a lot of spurious detection. So okay, so now we have everything. So the result is going to be saved into this table, xy f560w underscore tmp, this temporary table, and then to run this, we just type dsf f60w, so the instance just created, and the name of your image that, as I said, we are going to use the sky sub image to detect the sources. So if you go ahead and run it, it's quite fast. And here there is an overview of the table that has been obtained. So we have found 1,800 stars. We have different columns here. We have ID, the ID of the star, X and Y positions, sharpness, roundness 1 and 2. There are 3 parameters that can be used to understand how point-like your source is. So to discern between stars and galaxies, for example. Then we have mPix. This number of pixels being used by the kernel of the Starfinder to fit the 2D Gaussian kernel. Sky, as you see, is set to 0 in this case. Peak of the source, flux, and magnitude. As you can see, the magnitude here is defined in a weird way, as I reported here. So you might want to use it just for, to have a first guess of how of the real magnitude. We are going to refine it with the Aperture Photometry tools. So now, if you run this here, we can have a look at what we have actually found in our image. So if you go ahead and hit run, here you can see all these red circles are those that have been found in the image, and you can see we have found many things. It seems that we might have missed some pink stars, like here on this part here, but again, this is because of the threshold we set up. We missed all the many galaxies, and this is because the Starfinder, how it was set up right now, is going to be more akin to find point-like sources, or at least galaxies that have a point-like shape, indeed, like this one. But again, we can discern about that at the end using some of the parameters that I discussed before. Okay, so now we have a list with all the sources that are available in the image, and we can perform our Aperture Photometry using the Aperture Photometry function in phototils. So the Aperture Photometry wants an n times 2 array in which you add your positions that we're going to take from the table in output of the Starfinder. And then we are going to set up an object that's called circular aperture aperture that which defines circular aperture for each star at the position XY that we found before. We can run the aperture photometry with just one aperture radius, so we're going to obtain just one photometry, or we can use multiple radii. And in this specific example, we're going to use three that are all based on the full width at maximum of the PSF in this filter from MIRI. So here in the first line, we have to define this n times 2 array in the format that the aperture photometry is going to like. So to do this, we type np.stack x, so the name of the table that we just found before, and was underscore tmp. Here, the first column, that is going to be the x. Then we put the y, and then here axis equal to -1. Then in this line here, what we do is, again, we use the dictionary with the full width at maximum to obtain the full width of the PSF in this filter and set up the first radius. That's going to be R0. Then R1 and R2 are going to be equal to 2 and 3 times the full width at maximum of the PSF in this of this filter. And we are going to use these three radii to do aperture photometry with that. So next step is to define these circular apertures, and to do this, you can, as I said, if you do, we are going to do this for 3, and to do this in a fancy way, I found that we can type circular apertures. Then we type the position of the position array, that is the one we defined before, and then the radius of the aperture. And since we have 3, we are gonna cycle here for R in this upper radii, sorry for the typo, that is a list with the 3 radii that we selected before. So this is the way. So if you add just one, you just remove this part here, and and also this square bracket, and you put your radius just there. So now we have everything, and we can run the aperture photometry itself. So to run it, we just type aperture photometry, and this is going to be equal to first to the array where you're going to do this. So the data times this thing here dot area, and I will go back on this in a second. Then circular apertures, that is the aperture we're going to use, and then here method equal exact. That's going to basically this tells aperture photometry that if a pixel is only partially included in the aperture, it has to compute the right fraction of the flux that in that pixel is going to be included in the aperture and not the whole pixel. So if there are no typo and you go ahead and you run it, there should be a table in output from, okay, yes, there is a typo. Let me see. Okay, positions. Let me rerun. Okay, good. So here, you see, we have a table with the same length as the one that you had with Zero Star Finder. ID, X, and Y are the same as the one before. And then we have aperture sum 0, 1, and 2 that are the aperture, the flux within the aperture R0, R1, and R2 respectively. Here you see there are a lot of not a number, and this is because these stars, as you can see, are very close to the edges, and there is a high probability that on close to the edges there are some not a number flagged by our DQ array. So this is why we have this not a number, because again, aperture photometry just compute everything that is within the aperture. It doesn't care of what it means. Okay, so as I promised, I want to explain here why I haven't just used the data itself, but I multiplied it by this quantity called area. And so area is called pixel area map, and is something that is provided as part of the as an extension in these stage 2 images. So the area that is subtended by each pixel on sky varies as a result of the geometric distortion, which means that each pixel has a different collecting power. When you do the flat fielding, you take into account for a variety of factors like the physical different size of each pixel, the different response, and so on. And the flat fielding is designed to produce an image with a flat background given a flat stimulus. And So when you apply the flat field correction to your scientific image, the resulting image will be characterized by a constant surface brightness, but this is not true for fluxes. So because flat fielding does not take into account for the different collecting power of the pixels because of the geometric distortion. And I linked here also a nice description that has been provided in the documentation for the HST detector that you can have a look at if you were interested in learning more about this. And there are also some nice examples with a few numbers so you can have a direct feedback of what we are talking about. So when you do photometry on distorted, so unrectified images like the stage 2 images, the one that we're seeing here, you would like to use a field-dependent correction to your data. This is called pixel area map or PAN, to ensure that the sources will have the same magnitude regardless their position within the image. If you don't use that, it depends on the amount of distortion. If it is small, you might not have that difference between with or without using the PAM. If instead it is significant, then you might have difference in your photometry. Again, for the same star, or just observe a different position of your detector. So I know that it is a lot to take, but again, I provided this link here. This is very interesting and well described. Okay, so now we have done the first step of the aperture photometry, is this measure everything within the aperture. But now we are, as we said, we were interested only in the flux of the source, so we have to remove the contribution of the background. So to do this, we're gonna to define the background locally using a technique similar to the one that we just used to do the aperture photometry. But instead of using a circular aperture, we are gonna use a circular annulus within which we are gonna estimate the background. Okay, so this is the annulus aperture. So to do this, you just have to set up the inner and outer radii for the photometry. And to do this, we are gonna use 25 and 35 MIRI pixels. So the first thing we're going to do is to define this annulus aperture that is defined similar to what we have done before, annulus, and then position. It wants the positions, that is the one that we created before. Then it wants the R in is going to be 25 and R out is going to be 35. Then here, what this part here, what I do, what it does is just simply to use these the annulus aperture that we have just defined, use some of the properties that are available with this specific object to estimate a robust median value of the sky background within each of these annulus. So if this such a robust, it is well commented here. So basically, if this median value, if there will not be at least 10 pixels that can be used after all the different masks that we're gonna that are done available to compute the background, we are gonna flag the sky background to a very weird value, minus 99.99. So later on in this notebook, we will remember about them, and we're gonna flag them and remove from the from our table. So if you go ahead and run it, it should take a few seconds. Okay, and so we are almost there. So the work is almost complete, as I said, and we have everything, and just have to put everything together. And so first, let me make some order. And here I create a new table called Photo-Fi60W, and we are going to store a few values from the Earthstar Finder and the local sky background. Then we are going to compute the total background within each of the aperture that we used before. Then this is going to be equal to the local sky background that we just computed times the area of the circular aperture. So in pixels, so aperture, and then times 0. And here area, this is because this is the first, this is referred to the first aperture R0. Then the total flux within the aperture without the sky background is going to be Fi60W TMP. This is aperture 0 minus this quantity that we have just created. And that's it. So now we can go ahead and do the exact same thing for the other two aperture, just remembering to change the aperture extension. Yeah, I forgot the P. Okay. 2, 1, 1. Okay. So if you run this, okay, circular aperture is not apertures. Okay, I always forget the S. Okay, here we are. Okay, so this is the table that we just created. As you can see, we have these all the columns that we had at the beginning. So now we are gonna get rid of these not the number here. And to do this, we're going to run this cell. We're going to remove all those stars that have a medium background in the annulus that we computed before, flagged to that weird value I talked to you about, or that have a flux within the aperture that is, as I said, not a number. And here we are. So if you run it, you see that we removed about 200 objects from this list of detection. So now we can compute the instrument magnitude for each circular aperture, and this is going to be log 10, and then we're going to use F560W, that is the total flux, and it's going to be aperture R0 sky sub, and then the same for the other two. Okay, great. So here, what this cell does is just it looks into each of the aperture that we had before, and it looks at what is the DQ flag of each pixel. So if and then it will add a new column to the table that has a value that is equal to one of the DQ flag that's going to be within the aperture. This is just to keep track of who's who. For example, if you want to keep track if a pixel was partially saturated within the aperture, if there was a jump detection, so a cosmic ray that hit that source within the aperture, and so on. So if you go ahead and run it, you see we have a 1 star that seems to be saturated and 485 that has a jump detection. So if you run the next cell, we're going to look at how many of these jump detected stars with this jump detection flag within the aperture, and you see there are quite a lot of them. And again, cosmic rays are going to be something important to keep in mind when you plan your observation. You can see that they are evenly homogeneously distributed across the field of view. So now in the next 2 minutes, I will go rush a bit, but I want to provide just an overview of how to run these cells if you want to run them later. So the first thing I want to attach to the table, the equatorial coordinates of these sources. These are going to be useful for different things later in the notebook. So to do this, we use the WCS information saved into the ASDF extension of our image, so the advanced scientific data format that is available as part of the JWST model. So to do this, in this cell here, we created these two columns, and then we cycle through each of the objects in the column, and then we define this RD variable that is going to be defined as follow, the WCS dot transform. So we use this function within transform, and we are going to say it wants an input from where, detector, to what, so from the raw plane to the equatorial plane, and then it wants an input to the X and the Y position. So if you go ahead and you run it, and this line here is just because it will be useful for a plot at the end. Okay, so we are basically almost there. The last thing I'm gonna show you is the photometric calibration. To do the photometric calibration, we can simply cross-match our catalog made with on the stage 2 images with the one generated by the image 3 pipeline by combining all the images together. So the first thing I'm gonna do is to read this catalog as a table. So table read, and it's going to be defined by 60W 0. You see, okay, so there are a lot of columns that have been explained in the other JWebinars, the output of this. So we are I'm gonna skip the description of them. And so to do the cross match, we are going to use this function called match coordinates on sky that use the proximity-based approach to understand who's who between two catalogs when they are in the same reference system. In our case, we are going to do this in the equatorial reference system, so using array and deck positions. So to work, it needs to first store the coordinates of your sources as a sky coord object. And here I show you how to do that for our catalog and for the catalog made by the pipeline. And then you just call these match coordinate sky, giving the input to these two lists, and you will have three outputs. You're going to be interested only in the first two. The first one is the indexes of the second catalog that are closest to corresponding objects in the first catalog. So basically, this one tells who's who. And the second one is the on-sky 2D distance between sources. So if you go ahead and run it, it's very fast. And then you run the next cell. Here, we're going to have a look at the results. We're going to look at displacement in array cost deck and deck between the two catalogs. And as you see, most of the sources are centering the origin of this plot because we are working with the geometry distortion corrected coordinates transformed onto the same reference free system, so they should be more or less close to each other. And what you see here is just the reflection of their astrometric errors in their position. But you see, so most of the objects are here, but then you have a lot of outliers. So these are likely mismatches. So we are going to remove these and don't want to use this in the next part of the analysis. So to do this, we have to go here and just type Phot F560W, these 2D.arcsec divided by the pixel scale of MIRI is going to be lower than 0.0 pixels. So I'm going to use only the objects that are within a radius of 0.5 pixels in this plot. And then calib cat, that is the original catalog, index E2D, because we want to order it as the other one. And then we make the same selection. Calib cat, yeah, maybe I have to tell the name of the catalog. And y2d.cat, okay. Third is a charm. Okay, so now we have created these two subsamples from these two catalogs. And to compute the final photometric calibration, what we're going to do is compute the magnitude difference between our instrumental magnitude and the calibrated magnitude available in the this pipeline source catalog using the stars in common. So if you run this plot, this will take into account for the different things that I listed here in this description of the cell. So if you run the next cell, you will see the difference in the magnitude between the two sources, a function of the two catalogs, a function of the instrumental magnitude in our stage 2 based catalog. You see that it seems that just a 0 point value between the two. So if you go ahead and here, and you run this cell, what it's going to do is to take the stars that are brighter than this -3 limit, do a median clipped estimate of the 0 point. And as you can see, is -24.956. So if you go back for a second on the previous slide, you uncomment this line, you run it, you will see that this red line is set to the 0 point. So basically, it seems that we did a pretty good job. And so basically, that's it. So the final AB calibrated magnitude of our photometer is going to be our original magnitude. And for this specific case, I calibrated the one obtained with the R1 aperture, so mag R1 minus mag med F560W. And that's it. So now we also attach the calibrated magnitude to our catalog. So after this, if you see that there is an exercise in which the solution are at the end of the notebook, if you're interested in doing more or less the same things, but using another image. It has been slightly modified just to challenge you a bit, especially in the sky background, but everything is well described. And then there are two other bonuses that you can look at how to combine the two catalogs and how to do some selection.